So to help us understand this concept of an equilibrium, there's a virtual lab that I like to use every year because it does a really good job of simulating two things. One, what it really means to be at equilibrium, which means the rate of your forward reaction is equal to the rate of your reverse reaction. And two, it does a really good job of illustrating the fact that an equilibrium is constantly occurring. The reaction doesn't stop. It's what we call a dynamic equilibrium. So in this simulation, there's a couple things I want to point out. Our reaction is up here at the top. It's a really simple one. A makes B, and then B reverses back to make A. And then the reaction is going to take place in the box. And the gray bars here and this light blue line are doing their job to illustrate that energy diagram. So right now, our reactant side, the A side, has a higher energy value than our product side. So the fact that we would have to put in a small amount of energy and we lose a large amount of energy means that this equilibrium is exothermic. Okay. And so the letters up here are also illustrating the amount of A's and B's that are currently in the container. And over here on the right, we see that there's 0 and 0, nothing's going on, and then the numbers underneath the box, 0 and 0. So what I want to start by doing is plugging in 100 A particles. And so they do, like all particles do, they bounce off of each other, and eventually the particles hit with enough energy and in the right collision or the right orientation, and they bounce over this wall and go over to the product side, and their color changes from green to red, and they turn into these red B particles. All right, now I want to point out one thing perfectly clear. This is not how a chemical reaction actually occurs. There is not a little wall in a beaker where the particles have to bounce over. But this does a really good job of giving us an analogy of how the reactants have an easier time turning into products because they have a smaller energy value here, and the products have a harder time going back to reactants because they have a much larger reverse activation energy or a larger hill to climb to turn back into these green A particles. Okay, so right now I started with 100 A and 0 B, and I'm down to about 60, and we're losing, so 63, 62 A's, and the number of B's are starting to go up. So you notice that we lost a lot of A's initially, and now it's starting to slow down because we have fewer A particles to actually collide with each other and bounce over the wall to become B's. And every once in a while, some of these red B particles, because these numbers start to go up and the reverse reaction rate starts to increase, they now have enough to collide off of each other and they go back and make more A. Well, we're not anywhere near an actual equilibrium. Okay, we're getting close to the point where it's about 50 and 50, but even that doesn't really represent what it means for a system to be at equilibrium. All right, equilibrium does not mean equal amounts of A and B. Just by looking at the left side of the box, there's a smaller space, and the right side of the box, there's a larger space. So there's going to be more particles that stay over on the right side of this container. And again, that's equated to the fact that the reaction energy for B to go back to A is a lot larger. And so now we see that our tables have kind of turned. We've got more red particles on the right side, on the product side, and fewer green particles on the reactant side. And what it means for this system to fully achieve equilibrium is that every time one of these green particles bounces over to make an A particle, at the exact same time, a red particle has to bounce back to make a green particle, meaning that the rate of the forward reaction, A going to B, is equal to the rate of the reverse reaction, B going to A. And eventually these going to the right slow down because these numbers start to dwindle, and these going to the left speed up because these numbers start to increase. And eventually they reach that point where the rates are the same. And that's what it means to truly be at an equilibrium. So now that we've got a pretty decent understanding of what it means for a system to be at equilibrium, we're going to talk about a principle in equilibrium chemistry that was developed by a French chemist whose name was LeChateliers. And his principle was pretty simple. It said that if you have a system that's already at equilibrium, so that's key, it has to be at equilibrium, but if a stress or a change is applied to a system that's already at equilibrium, the system shifts to relieve the stress. Okay, so now that we understand roughly what it means for a system to be at equilibrium, what happens if we add in a new chemical or a new amount of reactant or product? What happens if we heat the system up or cool the system down? And what happens if we change the pressure inside the system and there are gases involved? So all of these things are what's referred to as possible stresses for a system, again, that's already in dynamic equilibrium. Okay? So we're going to be cycling back and forth to that simulation throughout the video, but I just wanted to illustrate what would the possible shifts be based on concentration, temperature, and pressure. Right? So again, we've got our equilibrium reaction here. This is H2CO3, that's aqueous, and that's in an equilibrium with carbon dioxide that's also aqueous, so this is dissolved into water. Well, what happens if we add more reactant that's already reacting to the right? Well, right now our system is pretty close to an equilibrium, so I'm going to pause it. What happens if I go and make this not 42 green particles, but 242 green particles? Okay, we've clearly got a larger amount of reactants now, and the likelihood of some of these green particles bouncing off of each other and flying to the other side of the container is greater than it was before. So we've now stressed the system that was at equilibrium, and it's no longer going to have equal rates of exchange. So how does the system shift? All of these green particles are going to bounce over to the right and establish a greater equilibrium, or reestablish an equilibrium as all of these green particles bounce over. So these are going to bounce over and make more red product particles, but then these numbers start to pick up and they bounce back to make more green particles. Again, the whole point is for a system to already be at equilibrium, and then we stress it and cause it to reestablish an equilibrium. Okay, before I added it, we had 242 green particles, and now we're already down to about 150. So the system is quickly reestablishing this equilibrium. Well, as we add H2CO3, we're going to see that the equilibrium shifts to the right. And the opposite, we're going to see that if we add CO2, equilibrium is going to shift to the left. So again, we have to remember that both the forward reaction and the reverse reaction are occurring at the same time. So if I add in a bunch of this forward reaction starts occurring more often because I'm increasing that rate. And then to reestablish the equilibrium, we say that the system shifts to the right. But at the same time, these reactants are going reverse to make that new product. And if I add more CO2, this reaction has a chance of occurring more often and will shift back to the left. So if I pause this system that's now at an equilibrium and I've got 174 red particles, what would happen if I eliminated all of them? Well, again, at equilibrium, we had two reactions happening simultaneously, A going to B and B going to A. Now the B going to A reaction can't happen. So the only one that's left to happen is A going to the right. So that's why the removal of a product is going to shift the equilibrium to the right. And so this forward reaction is occurring much faster than the reverse reaction until these numbers go down and these numbers on the product side start to pick back up and reestablish the equilibrium that was once there before. And so if I go in and take one of these things away, the reaction going from right to left occurs less often. So by removing CO2, we're actually going to shift the equilibrium back to the right. Right? And then if I throw a catalyst in there, we notice that the catalyst isn't actually included anywhere in the equilibrium. And we said that a catalyst lowers the activation energy. Well, if we lower the activation energy, this energy diagram, that yellow ruler in the middle is our activation energy. So if I lower the amount of energy here, the rate of the forward reaction picks up So a catalyst is speeding up the reaction, but it's easier for A to get over this hill, and it's still easier for B to get over the hill going back to the left. So by adding a catalyst, we actually speed up both the forward and the reverse reaction, which is why a catalyst always results in no shift to the equilibrium. So because we've increased the rate of the forward and increased the rate of the reverse reaction, adding a catalyst actually does not shift the equilibrium. Okay? In terms of temperature, there's only two things that we can do. We can either heat it up or cool it down by putting it on a Bunsen burner or putting it in an ice bath. And so in this equilibrium reaction, we're told that heat is on the product side, which means that this is exothermic. Okay, so if I add heat, I'm adding something that the reverse reaction needs. So by adding heat, I'm going to shift the equilibrium to the left. And if I remove heat, just like taking away something from the first example, if I take something away, this reaction going to the left can't occur as easily, so it's going to shift to the right. And then the last example in terms of pressure, it's super important to remember that pressure only affects gases. Okay? So in this equilibrium, pressure would affect something. In this equilibrium, because we've got gases, pressure would affect something. But in this equilibrium, because there are no gases included at all based on their current state, pressure won't affect anything with this particular equilibrium. Okay? So pressure shifts equilibrium to the side with fewer moles of gas, and decreasing pressure shifts equilibrium to the side with more moles of gas. What I encourage my students to do, it makes it just a lot easier. The side of the equilibrium, either the reactant side or the product side that has more moles of gas. This one has 1, 2, 3, 4 gas particles. This side only has 2. What I would encourage you to do is think of pressure as a reactant for this equilibrium. Okay? Because adding pressure pushes these gas particles closer and closer together, we're benefiting the likelihood of that nitrogen and those 3 hydrogens colliding. And so if they have a greater chance of colliding together, then that shifts the equilibrium to the right. So adding something on the reactant side always shifts the equilibrium to the right. And then if I remove pressure, just like taking away something on the reactant side, we're going to shift the equilibrium to the left. Right? So LeChateliers' principle is actually pretty straightforward. If we look at it as a generic equilibrium between A and B, if I add A, my forward reaction occurs more often, so my equilibrium shifts to the right. If I add B, my reverse reaction occurs more often, and my equilibrium shifts to the left. And then the removal of A and the removal of B do the opposite. If I take A away, the reverse reaction is still occurring at a faster rate now, so it shifts to the left. And if I take B away, the forward reaction is still occurring, and the equilibrium shifts to the right.